Hey folks, welcome back to Advent of Code in F Sharp. I'm losing steam as I'm doing a bit of home renovations, but we're still chipping away at the days. So currently day 18. Not a live code, but a recap again, because I had to use some mathematical formulas after some hints I got from colleagues. And it took me a while to get an intuition for those. So it was more drawing and noodling than it was actually programming for me, day 18. So let's take a look at what we did. 18 is the lava dip lagoon one with the trenches, and then we dig out everything inside the trench, and then we calculate the number of cubes that we dug out. So we could hold a whole bunch of lava. And initially when I started this, I was thinking, hey, we can use the point in polygon, the raycasting trick again. And I think that might have worked, but I did not feel like doing the logic where we have to calculate when a ray intersects with our polygon. So I did not feel like doing that because it was really tricky the last time we used it in one of the previous days. But then someone mentioned, hey, there's this mathematical theorem or two that you can use to solve this one. And without that one, I would never have solved part 2. So I think you no, I'm not sure. But if I look at the size of the numbers for part 2, I think you might have needed those formulas. So if you manage to solve part 2 in a different way than what I'm about to show you, please shout out in the comments below. Because I don't see how I could do that. But let's take a look at how I solved it. If you've seen any other solutions for day 18, you will note the two words called shoelace formula and Pick's theorem, and that's exactly what I used as well. But first time I looked at those formulas and I tried programming stuff with it, I was like, oh, what the hell is this? So I had to draw stuff to kind of make it make sense for me. So, what is shoelace in a nutshell? Shoelace is a very straightforward way where given a number of polygons, so a number of points in your space, you can calculate the area in whatever square units of the polygon constructed by those points. The only thing you need is the points have to be following each other in a roundabout way, one way or the other, doesn't really matter. And then it's just a simple addition, multiplication, or not even multiplication, a simple subtraction addition thing to calculate the area of that polygon. And at first I thought, cool, this is all I need for day 18. Turns out it wasn't. And it took a while before I could make sense of the why. So let's dive a bit into the why shoelace is not enough and why we also need this other weird Pick's theorem. In order to do that, so if you're interested in shoelace, and you're going to have to be interested in it for day 18, Wikipedia has a great article on it. It's a bit heavy on the mathematical side, but it's a mathematical formula, so makes sense. But what helped for me was drawing it out with an easier polygon, so an easier shape. I took 2 by 2 squares you can see here, starting at origin, 2, 0, 2, 2. So these are the coordinates you can see here. And then I just started playing around with those shoelace and with the trench calculations. So it's a 3 by 3 square. That means that there's 8 cubes on the trench and there's 1 internal cube. And if you take a look at what shoelace gives for these 4 corners of your square, it tells you like, hey, the area of this polygon is 4. So that's nowhere near 8 or 1 or 9. So I was pretty confused. But if you take a look at the actual numbers here, it's 0 to 2, 0 to 2. So it's 2 times 2. So it's kind of 4 in one way or the other. But that was clearly not enough to get to our desired count of 9 cubes in our pool. So shoelace was good to calculate the area in square units, but it was not good to give us the number of cubes. And for that, we can take a look at another theorem called Pick's theorem, and that is a theorem that says that if you have like integer coordinates, which we do, we have whole numbers, then you can easily calculate the area of any polygon by counting the number of polygons on the edge, on the boundary, and counting the number of polygons inside the, the number of points inside the polygon. And that's maybe something relevant because we already have the area and we have the number of cubes on the boundary. So the only thing that we don't know is the number of cubes inside. And once we have the number of cubes on the inside, the internal cubes, and we have the number of cubes on the outside, we can easily sum those because we have 1 here, 8 on the outside, 1 internally, and 8 plus 1 is 9, which is literally the answer we're looking for. So given our area calculated by shoelace, we can, and we also know the number of points in the trench, or that's easy to calculate. So we can reverse engineer the number of internal points. And if you know both these numbers, we can easily get to the desired result of total cubes inside and on the boundary. So that is why I'm looking at shoelace and Pick's theorem for day 18. Now let's take a look at the F# code. So there's some pointers here. That's just the input. I tried also for today or yesterday's puzzle, or day 17 or 18. I tried debugging F# code or F# scripts, FSX files, using Visual Studio. That was a rabbit hole. I will never, I will never attempt that again. No, that is like a pathway to hell. I did not get it to work. The only way I can debug F# code is to put everything in a F# project file, so my Visual Studio knows about it. I've found some references online saying, yeah, you can do it in theory. I even saw Don Syme, the brain behind F#, the godfather of F#, saying like, yeah, there's this way you can compile an F# script and then you can debug it. I could not get it to work, so that's something for another video, but I digress. This is a very clean way to also do some kind of debugging. If you have this function called debug, it's very similar to Rust's dbg debug macro, where if you give this an argument, it does nothing. So if you have a let binding saying, okay, this is x, y will have the value of x. So nothing seemingly happens, but there's a side effect. Debug prints stuff to the output. So that's also what I'm doing here with this debug function. You give it a message and some kind of value, and it prints out the message and the value and just returns the original value. So it's the identity function with a hidden side effect. And that is very handy if you don't have a debugger like I do in this setup. And if you just have a lot of these functional pipelines where you use this pipe operator heavily, it's somewhat tricky to debug. One, if you don't have a debugger, but two, also if you don't have like temporary variables in between and you have one big chain. But if you have this debug function, you can just plug it in anywhere. If I want to know what the intermediate result is here, okay, let's plug it in. Okay, I want to know what this is, I can plug it in. So you can just plug this function into any kind of pipeline to get outputs. It's not the same as using a debugger with breakpoints, but it gets really dang close, especially when you use heavy piping. So that's a nice trick to have in your tool belt, the debug function, or the debug macro, as in Rustlang. Anyway, that's another digression. Let's take a look at how we solved it using shoelace and Pick's theorem. As always, I parsed my inputs a bit to get out of string and character land. I defined a union type called direction that contains the 4 directions, and this is how I parsed instructions. I'm using longs here instead of integers. That's for part 2. Part 1, you could get away with using integers. This is code for part 2, by the way. It's almost the same, but instead of using really small numbers, we're using really big numbers, and then raycasting is off the table. You need to use something like shoelace and Pick's theorem. So let's take a look at how I solved part 2 with the really big numbers. Maybe a quick detour onto the problem description for part 2, sorry. It's exactly the same, but those hexadecimal color things in between brackets, they turn out to be encoded directions and distances. And those directions and distances are somewhat larger, as you can see for the example, you have this very, very big number. So it's exactly the same problem, but with much longer distances. So yeah, I parse those hex numbers. There's this system.convert to whatever you want, and you can give the base. So you can convert from binary, octal, hexadecimal, from any kind of a number system to whatever, to 10 base. So that's a nice helper function to know about. It's the .NET standard one. There's no F# sugar around it. This is to parse the directions, yeah. But then we get to the interesting part. I have a couple of 3 helper functions. One containing the exact implementation for shoelace, which is calculating the sum of the determinants to get a bit into the maths, but it's just shoelace formula to the letter. Don't forget about this division by 2. If you look at the Wikipedia page, it took a while for me to see this 2a here. So you have to divide your answer. And it makes sense if you start reading where this formula comes from. So yeah, this is the exact shoelace formula, and you give it the points. But if you take a look at what you have to provide for shoelace, it's the points, and the first point has to repeat. So the first and the last point have to be the same. And the way I built my trench, that I got that for free, but that's a detail you have to kind of know about. First and last point have to match, so you can create this matrix determinant thing, and you can see the first and last columns, they are the same. But that's applying shoelace to calculate the rough area in square units. So that's the 4 square whatevers we have in our 2x2 or 3x3 square example. And the number of trench cubes in the trench, that's also something we need to know about. The way I built my trench, I only know about the corners, the turning points. So I have to calculate how many cubes are in between. And I do that by just pairwising all my edges and then adding together the differences in x and y distance. So that's just one approach. You could also generate them. For part 1, you could generate all the nodes on the edge, but I don't think you could for part 2. So for part 2, you kind of have to do it this way, I think. Or you don't have to, but your CPU will like you better. That's a function to calculate the number of cubes on a trench. And if we know the area and the number of cubes on a trench, then by Pick's theorem, we can calculate the number of internal nodes or internal points. And this is literally, again, rewriting Pick's theorem to solve for I, so internal. This is Pick's theorem, the original version. And if you rewrite it, you get here, and everything just works nicely. And then this is my final calculation to calculate the total number of cubes. Given a trench, we do calculate the number of cubes on the trench, calculate the area using shoelace, calculate the internal number of nodes using pick, and then we can sum those two together to get our 8 plus 1 equals 9 for the example. Now let's take a quick look at how I built my trench. That's the last part of the puzzle. I also define some tape aliases. That I always like that over raw int and pairs of ints lists in my code. And then I have a couple of helper functions. One is to apply an instruction on given a current point. So that's just looking at the direction and applying the delta or the distance on the correct coordinate in the correct direction. And then finally a solve function that uses a good old fold, because we are building up state over a list of instructions, then it's always fold for me. And this is my folding function. So let's take a look here. Solve just parses my input to instructions. Then I build my trench, or the corners of my trench at least, using a fold. And this is our starting state, which is the first node we are started. I randomly chose origin, but this can be anything, but origin makes most sense, I guess. And the folder function just applies the next instruction to the current location, which is the first element in my trench corner list. And then I just append the next location to that list. And this keeps calling itself, building that trench list, or the list of corners of the trench. And once I have that, I can just do my shoelace Pick's theorem magic, and I get there. So yeah, it was a interesting problem, as in I learned about some mathematical theorems. If nobody pointed me to shoelace or Pick's theorem for the previous one with the raycasting, I would have never thought of using those. And I think if you have not heard about them, part 2 becomes nigh impossible, maybe? No, that's my question for you. Did you solve it using another approach, a more brute force way? And did it kind of work for part 2? I'm curious. But that's all I got. This is my recap for day 18 in F# using lots of maths. Not too difficult maths, but I needed to build some intuition with these drawings for me to get my head around it. So yeah, I had fun puzzle. I hope to see you tomorrow for more Advent of Code in F#. Bye bye.